What if an AI could actually learn to be better than its teachers? I mean, think about that for a second. Today, we're diving into something super cool in the world of AI. It's called offline reinforcement learning. And really, it's this whole new way of teaching an AI complex skills. But here's the kicker. It does it without all the risky trial and error. Instead, it just studies this, well, think of it like a textbook of experiences that already exist, and uses that to get to, you guessed it, superhuman performance. Okay, so let's make this real. Imagine this. What if an AI could learn to drive a car perfectly without ever, not once, touching the steering wheel? We're talking about it becoming an expert driver just by watching millions of hours of data from us, from human drivers. No crashing, no dangerous experiments out on the highway. That's the mind-blowing promise of what we're digging into today. All right, so to really get just how big of a deal this is, we got to take a step back and look at how things used to be done. Let's talk about the old way, the online learning loop. For like decades, this was pretty much the only game in town. It's a really simple loop, right? An AI just tries something out in the real world, it sees what happens, learns from that result, and then tweaks its plan to be just a little bit better the next time. It just repeats this over and over and over. It's this constant and, frankly, pretty slow process of trial and error. And look, this method is awesome for stuff like playing video games, where the stakes are low. But in the real world, oh man, it's a huge problem. I mean, you can't have a self-driving car learn by crashing into things 1,000 times, right? Or a medical AI that's just testing out treatments on real people. No way. It's way too slow, it costs a fortune, and a lot of the time, it's just flat out dangerous. So, this is what leads us to a much smarter, more elegant solution. Instead of all those risky live experiments, what if we just turn to the mountains of data we already have? It's like tapping into this hidden data goldmine that's just been sitting there. And this, right here, is the absolute core idea of offline RL. The AI learns from a dataset that's already been collected. It's fixed, it's static, it never, ever interacts with a live environment while it's training. It just sits there and reads that textbook of past experiences to figure out the best possible way to act. And you can imagine the applications for this are just huge. We can use data from human drivers, sure, but also things like medical records from past treatments or even old logs from robotics experiments. This is what lets us train these new incredibly powerful AI systems safely, efficiently, just by reusing data we already have. It's a game changer. But of course, it's never that easy, is it? When researchers first tried this seemingly brilliant idea, they just slammed into a wall. There was this hidden trap, this gotcha that made their AIs fail, and I mean spectacularly. And the whole thing boils down to one tricky concept: distribution shift. So, you're probably thinking the same thing I was. Wait a minute, we have these super powerful learning algorithms, and we have a mountain of data. Why can't we just put them together and call it a day? Well, the answer to that question gets to the very heart of the biggest challenge in this entire field. Okay, so here's the problem in a nutshell. Your AI is learning from this fixed set of data, right? But its whole job is to find a strategy that's even better than what's in the data. So what happens? Well, it's going to start thinking up actions that it's never seen before, actions that are not in the textbook. And that's where you get this mismatch, this distribution shift between the world it knows from the data and the new world it's trying to create. Let's go right back to that driving example because it makes it really clear. The data might have thousands and thousands of hours of cars just, driving perfectly, staying in their lanes. We call those in-distribution actions. They're what the AI expects. But that data set probably has zero, absolutely zero, examples of a car suddenly trying to do a U-turn on the freeway. That's an out-of-distribution action. It's a total unknown, and the AI has no clue what'll happen next. And this is the absolutely critical point. For those weird, unseen, out-of-distribution actions, the AI's guess about how good they are is, well, it's pretty much just a random number. The problem is, the learning algorithm is designed to hunt for the highest possible score. So it finds one of these random high scores for a terrible idea, latches onto it, and becomes dangerously, totally overconfident about doing something catastrophic. So, how in the world do you fix a problem like that? Well, the first idea that probably comes to mind is the most intuitive one. Just force the AI to stay within the lines. Make it stick to what it knows from the data. But, as we're about to see, that fix is, well, it's incomplete. Yeah, so this basic strategy has a name. It's called imitation learning. The idea is simple. If the AI is only ever allowed to copy actions that it's already seen in the dataset, then
boom, problem solved. It never has to guess about weird, unseen actions. Sounds pretty good, right?
But there's always a but, isn't there? Here's the catch. Imitation can only ever be as good as the data it's learning from, period. If you train your AI on a dataset of average drivers, you're only going to get an average AI driver. It can't learn to be better. And that's not the goal here. Remember, the whole point of reinforcement learning is to find the optimal way of doing things, not just to copy an average performance. Okay, so a slightly smarter way to do it is to filter your data first. You could, for example, take your massive data set and just pull out the top 30% of drives, the safest, most efficient ones. Then have the AI imitate that smaller, high-quality data set. And yeah, that's a better baseline for sure, but it still has the same fundamental problem. It can't invent a new, truly superior strategy on its own. And this is where the real magic of modern offline RL finally comes into play. Researchers figured out this incredible breakthrough concept that lets an AI create a strategy that is genuinely better than any single example it has ever seen in its data. They call it stitching, and it's such a great word for it. The algorithm literally learns how to find the best little pieces from tons of different examples in the data, and then stitch them together. So it might take the perfect lane merge it saw from driver A and combine it, or stitch it, with the perfect braking maneuver it saw from driver B, creating this brand new, almost superhuman sequence of actions that never existed in the original data. So how does it know which parts are the best parts to stitch together? Well, it uses this really clever mathematical tool called the advantage function. And you can just think of it as a simple score. For any situation, it tells the AI exactly how much better a specific action is compared to whatever the average action was in the data for that same situation. It's a better than average score. So with this new tool, the whole goal changes. The AI is still kind of doing imitation, but now it's a weighted imitation. It pays way, way more attention to copying the actions that have a high advantage score. Those are the proven above average moves. And at the same time, it learns to pretty much ignore the ones that were just average or worse. And, the cutting edge methods today take this even further. You've got algorithms with names like implicit Q learning, or IQL, and they use these really smart tricks to change what the AI is even trying to do. So instead of learning to predict the average outcome of an action, it can be taught to predict, say, the 70th percentile outcome. That basically means it's being trained to be optimistic, to aim for those better than average results, all from within that same fixed data set. Okay, so let's wrap this all up. What are the big takeaways? First, offline RL is incredibly powerful because it lets AI learn from huge data sets we already have without any risky live trial and error. Second, to make it work, you absolutely have to solve that distribution shift problem, basically by forcing the AI to stick close to what it knows from the data. And finally, the real secret sauce, the true power, comes from this idea of stitching, combining the best bits and pieces of what it's already seen to create something totally new and way better. And that leaves us with a pretty wild final thought, doesn't it? I mean, for pretty much all of human history, students could really only ever hope to be as good as their teachers. But with techniques like this, an AI can learn from a massive pool of teachers, all that data, and pull out a strategy that's better than any single one of them. So the question really isn't if it can become better than its teachers anymore. The real question is, what's the new limit?